So in this example, we're asked to determine the equivalent resistance for a circuit between terminals A and B. So here's our given circuit, and we have terminals A and B. So we'll be looking at the resistance in from this direction. And we notice our resistors are connected in what we call a Wheatstone Bridge configuration. So this means simply applying parallel and series resistor reduction really is not going to work here. So we're going to have to utilize something called Delta-Wye transformation. So let's see how that works. So with Delta-Wye transformation, if we have resistors connected in such a manner here, and we'll call this terminal 1, 2, and 3, then this will be lowercase r1, lowercase r2, lowercase r3. We can change the configuration to look like this. Again, where this is 1, 2, and 3. But this time we'll have a capital R1, a capital R2, and a capital R3. And our capital R's values can be written in terms of our lowercase r values. So for instance, R1, that's what's associated with this terminal 1. And so we see that the two resistors that are affiliated with that are R1 and R2. So we take the product of those in the top. And then the denominator is just the sum of all the lowercase r's. And so this would be the new value for R1 and our Y configuration. And this is true for any of the capital R's. We take the two resistors that are affiliated with that node divided by the sum of the remaining. So let's see how we can apply that to this circuit. So if we look at our circuit, we see that right here we have this delta configuration that we just mentioned. And so in this case, our lowercase r1 would be the 4 ohm, our lowercase r2 would be the 3 ohm, and then our lowercase r3 would be a 3 ohm. And then we're going to arbitrarily call this node here Z. So we have nodes C, D, and Z. So looking at that, we want to transform that to then a Y configuration. So we like this. So this would be node C, this would be node D, and this would be node Z. And so now we'll have R1, R2, and R3. So borrowing from what we defined about the relationship of these two configurations, R1 here then should be R1 times R2 over R1 plus, plus R1 plus R2 plus R3. So in our case, R1 is 4 and R2 is 3. And again, we'll have 4 plus 3, and then R3 is 3. So the denominator will be the same for each of them, so we don't have to calculate that every time. So here we get 12 over 10, and that's equal to 1.2 ohms. So that would be our value for R1. For R2, again, this will be R1 times R3 over the sum, which we said is 10. So then that'll be 4 times 3 over 10. So again, we get the same thing, 12 over 10, which is 1.2 ohms. So that's R2. And then finally R3, that's going to be R2 times R3 over 10. So that'll be 3 times 3 over 10. That's 9/10, or 0.9 ohms. So now with this, we can redraw our circuit. So again, we have terminal A coming across. These resistors stay the same. All right, so this is C, and this is D, So now instead of that delta configuration, we put this Y configuration. Like this. So now this is Z. And so our R1 was 1.2, our R2 was 1.2, and our R3 was 0.9. These resistors stay the same, 2 and 4. All right, so, and then this is still A and B. So now we've transformed our circuit. So with that, then we see that these two resistors are in series, and these two resistors are in series, so we can now rewrite that. So let's do that, combining those. And so when we do, again, we'll start with our A, we'll come over, and then we will have 2 plus 1.2 is 3.2, and then parallel to that, we will have 4 plus 1.2 is 5.2, and then that goes through this 0.9 ohm resistor back to this. So this is still A and B. Okay, so that takes care of that. So now we see that this, that this resistor and this resistor are in parallel. So we can do a little side calculation for that and say 3.2 in parallel with 5.2. That's going to equal to 3.2 times 5.2 over 3.2 plus 5.2. And when we calculate that out, we should get 1.98 ohms, just plugging that into the calculator. So those two then can be replaced. So now we come over here and we have this now is a 1.98 ohm resistor. Z is still here. We're not to Z yet. So then we still have our 0.9. This was BZ. And then this is B and A. So finally, we see that we have these two resistors in series. So we should be able to just add those together. So doing that, we have this left over, and we add those together, and we get 2.88 ohms. And so that's our equivalent then. REQ is equal to 2.88 ohms. And we got that. The only way we could calculate that was by doing that transformation.